the third speaker or from Penn State. We have Marcos Rigol, onset of quantum chaos and ergodicity in spin systems with highly degenerate Hilbert spaces.
Okay, well, thanks a lot for the invitation. It's a pleasure to be here. So I'm going to be telling you about the onset of chaos and ergodicity when you have highly degenerate Hilbert spaces. And really the motivation for this study is to understand what happens when you are close to regimes in which you have high fields or very strong interaction. So in that case, you are going to have degenerate spectrum. And then the question is, well, what happens with chaos and ergodicity? So, and I should say that this is something that we started thinking about like long time ago. With Lea, because in the early days of, state thermalization, those were regimes that people would look at to say, like, look, there are violations of ETH. And then I think in this paper, we pointed out that, well, you have to do some more work and have to look at the thermodynamic limit and how things scale. So today, let me tell you about this more recent work in which we've understood much better what happens and also how to control it. So now we have actually a way to control how rapidly chaos and ergodicity onset. So let me move this hand out of here. So this is the plan for the talk. I think half of the talk or even more is going to be on the introduction. So I'm going to tell you about the different indicators that we can use to figure out whether a system is chaotic or integrable, and also to find the transition between the two regimes. I will use all of them to discuss what happens in these highly degenerate Hilbert spaces. Okay, so let me get started with this more traditional level spacing and state thermalization, of which you can learn a lot on this review. So level spacing, right? So interestingly enough, we can understand what happens there just by solving two matrices, right? And you can simplify your life if you think of a system with time reversal so that those matrices are real. And then you can sample all those matrix elements with Gaussian distributions, right? And you want to know what is the probability of having some spacing. You have to carry out some integrals, so I'm going to leave that there for the students, change of variables, cylindrical coordinates. And you get this remarkable expression, right, which tells you a lot of what happens in those systems. So you see, the first thing is that as omega goes to zero, that probability vanishes. So it tells you that you have level repulsion. And then at high distances also vanishes because of this exponential, right? So now you can say what happens if I change this and make it complex and so on. Really, the main features remain. So the constant change, the power law change, but this remains, right? So now this is 2 by 2 with random, right? So you can ask what happens in physical models, right? And even in physical models like a spin 1/2 models, spinless fermions, or melodics that don't have a classical limit at least straightforwardly. So in some model, you're going to see different variables in this talk. So these are fermions hopping and interacting, nearest neighbor hopping and interaction. This model is integrable. You can write it as the spin 1/2 XXT chain, and this breaks integrability, right? And now you can say, okay, so, and you see that I set this to 1. So this is my perturbation. And you can say, like, okay, I take a finite system and I increase this, what happens, right? So if these are 0, the model is integrable, and the level spacing distribution is the Poisson distributions, right, on correlated random numbers. And then if you have this integrability breaking that is long enough, high enough, you will have something that is this Poisson, this Wigner-Dyson distribution, right? So they're very different from Poisson. And then in between, right, between this and this, you have something else. Right, a lot of this talk is about what happens with this something else as you increase system size, right? You have to ask yourself, is that always there? And actually, we already looked at that early on there. And you can take, for example, the peak that you get in the exact distribution and plot it as a function of this integrability breaking for different system sizes. And this is what you see, right? So as you increase the system size, you see you approach, this is the random metric theory prediction, and also you approach that value for smaller and smaller values of this integrability breaking, right? So just to say that already there we had the indication that in the thermodynamic limit, it will always be chaotic, right? So in this talk, whenever I say quantum chaos, I mean, you have something like a description based on random matrix theory for the spacings and other quantities, okay? Now then you can ask, this doesn't tell you about thermalization and so on. So for that, we need matrix elements of observables and eigenstate thermalization. And that we can also motivate the random matrix theory. So you can say, okay, so if I have a Hermitian operator, what does random matrix theory tell me about the matrix elements? Okay, so you can now write your spectral decomposition, write it into the eigenstate of the random matrices, which are random orthogonal unit vectors in arbitrary basis, including this one. And then you can start looking at what are the prediction of you average over eigenstates for the matrix elements. Now, to me, you define, because of this property, that the diagonals are really the average of the eigenvalues, and the diagonals are zero, right? So essentially, and you see this is just the average, right? So there is nothing that is essentially going to zero as you increase the dimension of your matrices. So you go a step further and look at what happens to the fluctuations. You find out actually that the fluctuations of the diagonals are related to those of the off diagonal by this eta in here, and they are suppressed, right? You can write it like this, and you see that they vanish as 1 over t, the dimension of the matrix that is going to be our Hilbert space. Okay, so and then from this, you can put these two together, and you get that essentially in random matrix theory, you could say you have a diagonal part that is large and the off diagonals that are suppressed, right? Eigenstate thermalization hypothesis is nothing but a generalization of that, in which now you have to account for the fact that you have locality and you will have a structure in any energy space. Okay, so you see, so the diagonal part now gets a smooth function that depends on the energy, and the off diagonals, they get, you see the random, you get a smooth function that depends both on the energy, you see here the average energy, and the energy difference, right, and the frequencies. And what you saw in there, this square is just captured here by this exponential on the entropy. Okay, so this is suppressed exponentially. This is supposed to be extensive in the system size, right? Good. So now we can go back to that question: what happens with eigenstate thermalization when you go to integrability? Or so I'm going to show you results now in 2 dimensions because this model is really something I will have in the back of my mind that I want to understand. So this is a transfer field easy model in 2 dimensions. And this one is antiferromagnetic, and it has some fields. So, through this talk, you will see statements about symmetries. You have to take care of all the symmetry. I'm not going to talk about them. So if you are interested, we can discuss or not. So this model has to limit, right? So if the field is 0, you have the classical interacting spins, or the easy model. And then if you have this 0, then you have spins in a field. And now when you're doing an eigenstate thermalization study, you need to decide what is the observable that you are going to look at, right? So you have to compute matrix elements. In here, we just took the antiferromagnetic structure factor, which is the order parameter for the phase transitions that happen in the ground state. So good. So this is now, right, it's a BC plot. It's a lot of information. So these are, you see, the matrix elements, the diagonal as a function of the energy, and then there is some normalization here because you are changing coupling constants. And there is something here is increasing the strength of the field. Okay, and now you will see in colors resolve for different system sizes. Okay, so you see something like this in the classical limit. There is no eigenstate thermalization. You see there are a lot of degeneracies because you see few points and nothing that is a smooth function of the energy. In the strength field, the same, right? So you see very large bands in here, and then as you move away from here, you get regimes like in here, which you see different system sizes. You get something that is becoming smoother and smoother. So you see the support is shrinking, and you see you are changing a few sides. That's already telling you that it's shrinking exponentially fast with increasing system size, right? As we saw from random matrix theory. Now, the other thing that you want to see is that as you move toward these other ergodic regimes, right? You see that if your system is not large enough, you see a lot of fluctuations. Like, let's take a look at this one. But as you increase the system size, you start seeing that it's becoming smoother and smoother. And that was something that Lea and I were pointing back then in terms of quantum chaos indicators, that you see that this is moving towards stronger fields and this is moving toward weaker field, and essentially in the thermodynamic limit you expect everyone to be ergodic. Right? Today's talk is about understanding what's happening in this region. Good. Now there is something amazing here. So you see In this expression, a random matrix theory cannot tell you anything about the structure that we have in there, right? So that structure is beyond random matrix theory. But now you can come in here, so you see you don't know that is the function of the energy, right? And also this function. Now you can come in here and do the ratio of the variances of the diagonals and of diagonals that I was showing you that is related by that eta parameter in the random matrix theory. And this is really, when you see it for the first time, you say like, wow, I cannot believe it. So I'm going to do it for this system, actually in the maximally chaotic regime. And this is what you get. You take the difference, okay, of the diagonal of diagonal, the entire spectrum, 170,000 states, and you see that it's really fluctuating about the value to the random metric theory predicts. Okay, so even though you cannot get the structure when you remove you're computing that ratio, and it's in the entire spectrum except at the edges. Okay, good. So all this is just to say that we can characterize the ergodic phases and the non-ergodic ones. Now, these indicators are not great if you want to understand the transition between them, right? So you saw things were moving. And that's where this typical fidelity susceptibility has like helped a lot. Right, you've probably seen that last week because Anatoly was around. So this typical way of defining typical in here, they use it in the context of disorder system, and you see it's the exponential of the average of the logs. And what you want to do is remove a few values that may be, a few fidelity susceptibilities that may be extremely large, that if you do a regular average, they will kill your average, right? And then the fidelity susceptibility is actually a null quantity. This is the definition in here. It was actually introduced by Zanardi, you see, in the early 2000s, and they were thinking about identifying phase transitions in ground state phase transitions. So it was something that I got interested in shortly after in the context of ITC superconductivity in the TJ model. So you perturb with D channel, S channel, and so on, and you look at whether the model is susceptible. Okay, but now we're going to be using it in the context of very highly excited states. Good. So now I'm going to get back to the same model I showed you before, some terms for simplicity. I am going to add irrational coupling constant because the integral has rules of unity and very special points that I want to remove in there. Okay, so I'm going to start with this model as I change this delta, and I'm going to look at this quantity to see whether we can identify what happens with the onset of chaos. Okay, so these are technicalities of how we do it, but the important thing is that because we have ETH, we can predict how this chaos in the let's say ergodic phase, and we can put that already inside the fidelity susceptibility, so we can rescale it. So this is the sort of behavior that you have. I put two observables just that you are sure that this is not fine-tuned, that we spend months figuring out which observable to do it, and so pretty much you have to fine-tune not to see this. So this is the kind of behavior you have. So you see, so if delta is order 1, you get collapse for, these are resolved for different system size. That's where the system satisfy ETH, because by hand, I put this scaling so that there is collapse, right? And then you see that when you go to smaller values of delta, what is it that is happening is that the susceptibility is good, and then it's right, and there is a maximum. Then you increase the system size, I put off here, the system size, and in the thermodynamic, you expect this to go and diverge, right? There will not be oversight in the thermodynamic limit, and you see the same happens on both. And now you can ask what's happening with this peak. You can ask the scale, the susceptibility, and the location. So if you look at the scaling, you find out that it's scaling as 1 over the average level spacing square. Okay, that is omega Heisenberg in there. So this is diverging, and this is the fastest that it can. And in all models that we looked at, we find this behavior. So this seems to be universal. So the next question is what happens with the location, right? And now again with this omega Heisenberg in there, we see that seems to be polynomial in that level of spacing, so it's exponential in the system size, and you see that it's vanishing really fast, so exponentially. So this point is moving towards 0 exponentially fast. Okay, so that from here, then we say like, well, then you need exponentially small perturbations to break integrability in finite system. But of course, you have to remember that this is diverging. So in the thermodynamic limit, when your perturbation is very small, there will be some very long time scale that will show up in your problem. So good. So that's now a way that we can look at transition between quantum chaos and integrability. And this is, since there have been a lot of discussions about disorder, then we decided to take a look at, let's take the Anderson chain and play the same game, right? So now we put the Anderson, this is written in the spin language, but this is just free fermions hopping with a disorder potential. And you see what we did the hopping and the disorder, the width of the disorder is to be ordered 1. Okay, and then I can ask, what happens when I introduce the interactions, right? So you do the same game and you get something that is very similar to what you get for integrability. Okay, so from this plot, then you can look at the scale of the peak and of the location, and you find out that it's very close to this 1 over omega squared, and this one is very close to be either exponentially fast or very high power in the system size. Okay, so that from this, what you could conclude is that this Anderson model in this regime, in which the localization length of the non-interacting model is a few lattice spacings, then it's not stable against interaction. Okay, so of course I cannot distinguish going to 0 from going to 10 to the minus 16, but at least we don't see any slowing down. So it's something that may be very small. Yes.
What is the localization length?
Yeah, it's about, yeah, that's 5 or 6, right? We have big discussions. It's 5 sites. Yeah.
So your system size is 3 localization length.
That's correct.
And you don't see
We don't see any effect of it. Yes, that's right. Right. Well, but these are exponentially, right, growing things and changing. So that's right. So
this is, I mean, measured in units of localization length, your system is straight.
yeah. And it's changing, but you don't see any slowdown. So I think you would expect to see some form of a slowdown. That's right. But look, I mean, the whole point here, you can see the value, right? So definitely for these values, right, of delta, you will see something that is ergodic.
Of delta, the first thing that could happen, that does happen, is that the localization length actually becomes even larger.
Yeah, that's true.
So your system size is effectively very small.
That I totally agree. But you see no indication, that's right, of any localization in there. And there are different ways. I mean, you want to ask about what localization length you are interested in and so on. So, but yeah, that's right. Good. So that's just a side just to tell you, those that work in the awaken. So the other thing that is using a lot recently is the entanglement entropy, eigenstate entanglement entropy. So and this is a way to move away from observables. You have something that is observable independent. Okay, so we have this tutorial that you can look at. So what are the frontiers on this? Is really the effect of, let's say, symmetries on the entanglement. So with Leo, we started, when Leo was at Penn State, we started looking at the effect of U1 symmetry and in spin 1/2 systems. And now this is figured out for any local Hilbert space. And more recently, we've been looking at what happened with SU2 symmetry, but that's not what I'm going to be telling you today. So let's see what happens with entanglement entropy of these models when you go to the integrable or non-integrable limit, and whether it can tell you that the system is ergodic or not. So we took this model just because the model has essentially all models that you see around that people study to look at integrability and chaos. So not a big deal to look at all the parameters. We optimize it to find the most chaotic point. But in here, the important thing is that you can control whether the model is integrable or not, and you can control whether the model has U1 symmetry or not. Okay, so that's and then we are going to pick up one integral regime and one chaotic regime. So now let me tell you about the two cases in which we have some analytic controls.
Marcos, yes. Question related to the discussion that you had with Fernando before. What prevents you to go to larger disorder, reduce the localization length, and so in?
That's right. So what prevents me is nothing, and I could do it. Right. But it's that I was telling you the strong field. So you start having a stronger final size effects. Okay, so you can use larger, right? So I can tell you what happened with the early days of there is violation of ETH, right? So someone would put a brutal field interaction, right? And then at that point change the system size and tell you nothing happens. This is non-ergodic. But that's of course because you have an ergodic phase that is growing and you're very far from the regime which is growing, so you don't see it. Okay, so all we wanted to say is like, let's take order one parameters, right, where we have everything well controlled and so on, and let's do a calculation. As you increase this order, then final size effects are going to become stronger and so on. But that's
on the other
hand, yes.
On the other hand, the problem is that to have an order one parameter make the localization length long, and so
I mean, it's long. It's it's emphasized. It's not 10 times. And you can see no effect of that. That's
okay.
But that was a choice. We purposely took it there. So we just want to be in a regime in which there are no large parameters, right? So no perturbative expansion there. Yes. Good. Other questions? Good. So let's come back to this, and there, this is important, and that's why in this talk I was emphasizing this, because we have to distinguish localized system from integral or non-interacting system. So, and the entanglement is one of those quantities that tells you that there is a big difference, okay? And so let me just go about this. So if you have this is what is known as the page curve. That's what you expect for quantum chaotic systems, random matrix theory, and so on. So notice this is the average the length of the system. So if this is order one in the thermodynamic limit, it tells you that the entropy is scaling with the volume of the system, right? Because I'm dividing by L. Okay, so I'm looking at the volume scale of the system, and from here, I'm already advancing that chaotic system is going to scale with the volume. It's going to be maximal. It's going to be essentially the maximal possible scaling that you can have. And now, free fermions, right, and that's a misconception, is also going to be volume law. Okay, so it's different from localized system. Localized system is just going to be order one, right? So free fermions, which are not ergodic, have a volume law entanglement, but is maximal. So this is the result for free fermions. On top of that, the slope depends on the fraction. So remember how this entanglement is computed. So you take a subsystem, system L, and you trace out everything that is outside some L8, right? So this L is the subsystem size. Okay. So it depends on that fraction. So now you can take the model I showed before and and you get these plots, right? And if you do the integral interacting again without you get these plots, right? So this one is close to page, but not page. It's a finite system. And this one is close to these non-interacting fermions, but again, not on top of it. So you want to do the scaling. If you do the scaling, you see that the non-integral case is going to 1, right? So this is going to this point in the thermodynamic limit. And if you do the integral, it doesn't go up. It actually goes down and it approaches this non-interacting fermion. So here there is universality to the page result. Here there is no universality. So you get something that in general will depend on the model, but is going to, all the models that we've looked at is around this 0.55. Okay, but the big news is that it's going down, not up. Okay, so it's very clear that the integral interactive models, right, are different from the quantum chaotic ones when it comes to entanglement, not because it's not low, because it's not maximal. Okay, they are all very low. If it will be low, then this will be 0. Okay, good. So that's all the background. And as promised, it's more than half of the talk. So I can take questions before we get now to the model, if there are questions about that, those indicators. Okay?
Try to understand.
Yes.
Is there some understanding why integral models go to free fermions?
This is an excellent, so the free fermion, we can understand why it's volume and why it has that shape, right? And why the integral interacting is going to that regime is something we are actually working right now. So we are working on that. So
Is it all?
It's not published, huh?
Is it all integral? So
All the ones that we have studied.
the linear would also go to the same.
When there is not a Lattice model, and then you have to solve problems. So these are finite Hilbert spaces and so on. So in the zoning models, complications, right? But yes, so that's right.
1D.
Huh?
They're all 1D.
These are all 1D, but
So they can
what cannot be Fermionized?
they can
They cannot be Fermionized. That's right. That all see, they are quasi-particles. That's right. That's correct. Yes. That's one way to understand it. But it's interesting that it is irrelevant. The interaction become irrelevant in this case. Yeah, that's the picture. Yes. So yes, go ahead. Yeah.
The like ground state and black.
That's okay. Good. Excellent. So thank you for asking that question. So again, all these, or as a matter of fact, all these results, right, for integrable models, we average over the entire spectrum.
Okay.
So ground state and so on is no, this is typical states in your spectrum. Yes.
Okay. No, fine. Good.
Right. So that's right. It's the entire spectrum. These are high energy states. Okay. Very important. That's right. Question.
So how typical is this typical? Sorry. How typical is this typical curve for integrable systems compared to how typical it is for chaotic systems? Do you need to do more?
Excellent. So typical. Yes, you have exactly. Yes, excellent. Actually, I think that slide. It was excellent. So the variance is exponentially small in the quantum chaotic models, and it's vanishing in the integrable models, but polynomially fast. Okay, so that's an excellent. So that's another way to distinguish integral from non-integral. The variance in one is exponential, the other one is polynomial, but it's vanishing. Indeed, this is typical in the thermodynamic limit. That's an excellent question. Okay, other questions? Yeah.
I think as the integrable models should approach non-interacting fermions because you can find a transformation.
Yeah, this is what they are saying. Yeah, but you need quasi-particles and so on, and then see this is general or not. One has to
So
think.
these integrable models are integrable by beta ansatz or something.
This model.
Okay, so I would say that there is a transformation that bring to an.
And that's right. That's the intuition, but
Okay.
you have to put
Okay.
it. Yes. Okay, good. So related to the case of Degenerate. So this is the model I showed you before, the transfer field icing, and now notice that I'm going to set the field strength to 1, and my perturbation is going to be the interaction, right? So now I'm going to this guy, right? And you see that it has two types of terms that conserve magnetization and terms that break magnetization. And this is essentially what we need to understand is when you make J non-zero, what happens with the system. So instead of doing this in the square lattice, because it's very hard to do scaling and so on in 2 dimensions, so I'm going to put it in 1-dimensional lattice, okay? And I'm going to remove the magnetization preserving terms because I want to slow down the ergodicity as much as possible, and that's this node that I'm telling you that you can start now controlling at which order in perturbation theory your perturbation will start acting on these guys, right? So good. So this is the model I'm going to be studying, and you see I need to add next nearest neighbor because in 2D this guy is not integral, but in 2D if I want to keep this so these terms are needed there to break integrability. Good. And then I'm going to show you, for example, what happened with the average of consecutive, the ratio of consecutive level spacing. So this is the first thing that is remarkable in here, right? So you look at that average as a function of J, and you find that is the GOE prediction for all values of J. So it doesn't matter how small your J is, 10 to the minus 6. You will get level repulsion. And you go to large values, you get the same. So essentially, if you look at this indicator, this model is quantum chaotic from any non-zero J. Right? So against the intuition that I was telling you that it's like a SUA that you need to be very strong, you need to perturb this very strongly to be able to get ergodicity and quantum chaos. So it's not the case. But something is happening here, and just purposely put a lot of point there so you see that this indicator doesn't capture it. So if you look at the entanglement entropy, the average, you see that it's large, you get a plateau in here, right? So these are 2 different system sizes. You get a plateau for very small j, plateau for very large j, but there is a crossover. Actually, this crossover is very similar to the difference that in that show I was showing you between magnetization preserving and magnetization breaking. So it's a very small difference. So this is the order of the difference. So this is already telling you that it appears to be chaotic everywhere because the value is large, so you see very far from 0.55, but something changed, right? And now to understand this regime, we can do the general perturbation theory using the Schiffer-Wolf transformation, right? And in here, what you need to work, right, is to find this anti-Hermitian operator, and this is how it's done. In general, right, your Hamiltonian is sum on perturbed path and the perturbation, and you want to kill the linear terms in the expansion, so you choose your anti-Hermitian operator so that when it commutes with H naught, it gives you the linear term, so it kills the linear corrections, right? And then you get the first correction is G squared because S is order G. Right, so in this model, this is your anti-Hermitian operator, so it looks like this. And now when you run into the Schiffer-Wolf, you get this Hamiltonian. And you see that essentially what that perturbation in this order is doing is like you have some correlated hopping. So you can think of this as hopping, right? And this as some occupation in the site. So this introduces some correlated hopping. But what is the important thing that we learn from here? Things. The first one is that this guy is a quantum chaotic model. Okay, so that's it. So all is a quantum chaotic model and some offset of the energy. And the second one is that the energy scale for your interaction is J squared. And now you can go back and do the calculation with that model, and you see that in this regime, of course, they match perfectly the exact numerical calculation, and something happens in here, right? So it goes down. And what happens in there is, of course, that you see in this limit, you have these bands, right? Like energies are dictated by the magnetization. And because of that Schiffer-Wolf Hamiltonian I was showing you, they start broadening J squared, right? And at some point, you're going to hit another band that is over away, right? And they hybridize. Now, your exact calculation will notice that, but of course, the Schiffer-Wolf one will not see it, so they will go through it, and that's why you lose level repulsion, and that's why the entanglement entropy goes down. Okay, so this is happening when those bands start to overlap. That's when you start having ergodicity. Yes.
Feeling where it goes.
Yes, I'm going to show you that. Of course, that's the exciting thing. So, good. So then you can, for example, the magnetization around, you see that Schiffer-Wolf, of course, tell you that it's conserved. The exact calculation is just small line, but you see that there are no, there is no really big hybridization that states that are in between these things. So it's pretty well conserved in here. And then on the other side is a smooth function. It's like eigenstate thermalization, right? So you can go to the eigenstate thermalization, right, probes, and you can look at now at the entanglement entropy of eigenstates as a function of the energy, and you see you can do the exact calculation, and the Schiffer-Wolf, they are almost on top of each other. You see really close to where this hybridization start to happen, and this works very well. And if you go larger, then you get ETH. Right? Now, this is important in here. This is, you would say, ETH within the bands, breakdown of ETH in the entire model. Why? Because remember that all these bands are order one apart. Okay, they all belong to the same microcanonical window in a large system. Okay, the difference between them are order one, so they all belong. That's why when I show you those plots of eigenstate thermalization, you would say like, oh, there is no eigenstate thermalization. You have those lines, right, that you saw in there. And you can do all observables, I don't know, next nearest neighbor, SC, and you get the same. Okay, so I think by this point, I think we understand, right, what is happening. You have the full Hamiltonian doesn't have magnetization conservation, is ergodic, right? The Schiffer-Wolf has magnetization conservation and is non-ergodic, right? But it satisfies ETH within the bands, right? So now is the question. So what happens in between? Right? And to understand what happens in between, we can go back to this typical fidelity susceptibility and then look at different system sizes, right? And this is why I'm doing in 1D, because in 2D, I would have trouble doing any scaling, right? So the first thing is you see the same thing you had seen before. You have some peak that move all. If you look at the scale of this maximum, you see it appears to go towards -2 in the thermodynamic limit. Actually, if you look at the current prepping version, you will find that it's -1.8 because we put 3 extra system size in the calculation. So as you start cutting down the smallest system, you see that that this is becoming closer to -2. Okay, so
here there are 5 points, there are 3, so you are adding.
no, I did 3, there were 8 before. Yeah.
Here, so let's say the 2 more points are 18 and 16.
So what do you mean? No, this is the largest point is 22, 21, 20. There are consistent. Of course, there is 19, and 16, and 15, and what have you. Yeah, that's right. This is the scaling of the peak. No, this is the maximum. Okay, so wait. This is the maximal fidelity susceptibility, right? So I'm just saying it's diverging as 1 over omega squared.
It's on the left from the maximum.
That's right, and but there are 2 things we can look at: the maximum, the scale with the system size, and the location, the scale with. The location is this one. Is this one, and now this is the great news. I mean, here, well, great news, and it's essentially why is everything looks so slow compared with integrability. It's polynomial L. Okay, so it's here it looks like L to the -0.8, right? So for those 5 system size. As a matter of fact, now we can predict what is the fastest that it could move, right? Because that's determined by when the bands overlap. Maybe it's slower because maybe and just the bands touch. You need something more. So we can make that argument. So you see, within each magnetization band, right, the support of the spectrum is proportional to the system size, is a local model, right? And to the energy scale J squared, right? The bands are order 1. So you would say, okay, so for them to you need J star squared times L, that is something order 1, right? So that tells you that the fastest that it can scale is 1 over square root of L. Now, if you look at the plot, I showed you 1 over L to 0.8, but of course, this is the leading term, right? There are other terms, 1 over L to the 3, and in finite systems, they make it look faster, right? But this is the fastest that we expect, okay? So in that sense, that's why in finite systems, right, you would say that is a slow, ergodicity is slow to onset because you need large systems. You need for those bands to overlap. Okay, so that's the story, and you can ask, okay, how do the spectral functions, right, that f of e omega that I showed you for ETH look in these systems, right? So that's what I'm going to do next. I'm just going to plot that f function and just using this particular regularization of the delta function. Okay. So this is how they look like, and maybe seeing some spectral functions before in this workshop. So if you are on the small, right, this chaotic phase, you see that you get a plateau. I think this is a typical form of the spectral function that people show to talk about Taoles energy and so on. So if you go to the J star, then you see a divergence, right? And remember, in the thermodynamic limit, right, this guy is going to be inside this curve, right? This in the thermodynamic limit doesn't exist, right? This is on the left of the peak, and the peak in the thermodynamic limit is all the way to 0. So in this regime, essentially, everything is going to look like a spectral function that is diverging. Okay, and that's where all this slow thermalization is going to be encoded. And then large J, you get again something that is flat, as you expect for chaotic systems. Good. So that's how it looks like, and keep in mind is as J becomes smaller, right, that spectral function is diverging, and time scale for thermalization are going to become slower and slower. Okay, good. So now we can go back and say, okay, this is what I started. Really, I started with, I wanted to look at the transfer field is model on the square lines, right? So we can do now numerical calculations for this and see if it matches our expectation, and this is how it looks like. Okay, so this peak is the one that we study in the 1D models. Okay, so then you see there is this regime in which you have ergodicity, and now in this model, of course, when J becomes very large, again you go to another like a classical regime. You go to the easy model, and that's the other peaking here. Okay, so but of course in the square it's very difficult to study scaling with system size of this peak, which is why. But the physics is the same. Definitely there will be a changing here in the scaling because this linear term already contributes at first order in perturbation theory. Okay, so with that, I'm done. We have time for discussions and so on. This is what I want you to take out of this talk. So if you have this system with very straight fields or interactions and so on, you can have degenerate spectra, and chaos can emerge for arbitrary small perturbation. So there will be level repulsion immediately. So there may be lack of ergodicity, and that's just a finite size effect, right? That it could be, for example, because some quasi-conserved quantities, in that case was the magnetization, right? And that there is a crossover that is marked by this divergence of the fidelity susceptibility. And in these models, right, is polynomial with system size, how that moved to zero, right? In models that are integrable, interacting models, and hypertrophy, I showed you, is very fast, okay? So again, with that, let me thank my collaborators. Mahmoud just moved to Texas A&M for a postdoc. He's a postdoc. He's Brazilian, so he's a postdoc in my group a long time ago, and now he's a professor at the University of Houston. So they were the guys doing the hard work in there. And thank you for your attention.
Good questions.
So if you had a system with like SU2 symmetry that was thermalizing, would you see the same peak and potentially same scaling if you added an SU2 breaking perturbation?
That's something that we are studying. That with what happens, right, when you break non-abelian symmetries. Okay, so that's but yeah, that's
Because then you have like a degeneracy, but maybe not like necessarily extensive, right? But you have these multiplets.
That's right. So the SU2 symmetry, SU2 is closer to one. I mean, of course, there is the non-abelian character, but it's closer to that spirit, which is the kind of thing that we are looking at here, right? So this is a This is a breakdown of a U1 symmetry, if you want. Okay.
So I guess the same applies for Hubbard models at large U.
That's right. That's right. And that was those Hubbard model at large U was one of the first models that people say like, oh, this is a violation of ETH. That's right.
Yeah.
That's right. The same apply. You get those bound with you.
You can get probably the same scaling.
Probably the same. Yes. You can probably understand it and so on. Yes, that's right. Yes.
Thanks. So if you look at the spectral function of your quasi-conserved quantities, or also like your quasi-conserved quantities dressed with your Schrieffer-Wolff generator, do you see something interesting there?
Yeah, we haven't looked at that. But so what would happen with that spectral function? So in this case, would be the magnetization,
Yes.
and yeah, that's an interesting question. Yeah, we haven't looked at it. Yeah.
Thanks.
So indeed, so this I should say that's a good point. So what is the observable that we are looking in here? That's the perturbation. Okay, that's right.
Okay, if not, we can thank Marcos again.